Ah, sweet mother of statistics, we're finally getting ready to wrap up our discussion of descriptive statistics. So last set of PowerPoints, we talked about the empirical rule, right? That 68, 95, 99.7% rule. We talked about the mechanics. We sort of focused on sort of mechanically applying this rule. We did some examples. Perhaps, hopefully, you worked on some homework problems or talked to someone if you were struggling with it a little bit. Now that we've sort of got that behind us, we're going to move from mechanics to implication. So we're going to start talking about a little bit more of why do we care about this empirical rule. What is it bringing to the broader field of statistics? What is it bringing to the broader field of research? Because we'll see this empirical rule kind of allows us to create this kind of z-score, at least as part of this kind of number sense or statistical sense that feeds into this concept of z-score, which is really a very important underpinning or foundation of statistical research.
And so, as I said, let's look at another set of examples, and these will hopefully illustrate those aforementioned implications that I was talking about. So, now let's make this even more fun. So just to showcase the wide realm, the broad spectrum of situation or context for which statistics can be helpful or useful, let's make this a parenting example. So let's say, may or may not be role-playing for you, that you have two children. You have child A and you have child B. So child A had teacher A for math 121, and they come home for the end of the semester and they're all excited and they say, "Mom or Dad, I got a 75 out of 100 on my final. I know you're proud of me. I worked really hard for it. I want you to cook me a big celebratory birthday-style dinner to celebrate my accomplishments." But just as child A is saying that, oh dear, child B pushes his or her way into the kitchen and says, "Whoa there, hold on, wait a second. I got an 80 out of 100 on my final," right? Different teacher. And that means that I did better. So I want my exploits to be celebrated. I want my big celebratory birthday style dinner. Now, of course, a birthday this big, this elaborate, you really only have enough time to cook it for one of them, as much as you would like to celebrate the accomplishments of both children. So you need to pick one, ideally in a statistically defensible, aka diplomatic way. So which child did better? Which child gets their birthday-esque style celebratory dinner? Child B, huh? That's an interesting choice. Let's take a look at another example. Remember these two scores because they're going to be the same. So child A got a 75, child B got an 80. 75 and 80. Now, what if we pick child B and child A says, "Whoa, whoa, 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 stop the clock. Why don't you wait a second? Test scores in my class," and I use that word normally distributed. Normally distributed just means they have that symmetric bell shape to them that we talked about in our last PowerPoint. So student A says that in my class the average score was 70. I scored a 75. That means that I did above average. Whereas my sibling, child B, right, had that same bell-shaped distribution, and more importantly, the average for that test was an 85. Which means that child B, who got an 80, did worse than average. Right? So child A certainly has a point when they say, all right, technically in a direct comparison, my score, yes, is less than my siblings. Nonetheless, I took a much harder test and I did above average, whereas my sibling took a much easier test and did below average. And do you, as a parent, truly want to reward sub-mediocrity? Oof. That's a pickle, isn't it? I think, at least, student A has a point, and maybe we would want to reconsider, right, who gets the celebratory birthday style dinner. Now let's try a third example to make things even a bit more challenging. Both students have a 70. Oh dear. And the average test score for both of their exams is 60. Oh dear. This is going to be a challenging decision trying to pick which one gets their birthday style dinner. Both of them, if you were to make a histogram of their test scores, would have that nice symmetric bell shape. That's what it means to be normally distributed. The only difference is the standard deviation of test A is 5 and the standard deviation of test B is 10. And so my question to you now, as a perhaps real, perhaps imaginary parent, is how can we use our shrewd knowledge of statistics to determine which child did better, and hence which child is going to get their big celebratory birthday-esque style dinner. Student A, huh? Well, you're correct. It is student A. Let's explore why that's the case. Let's start by asking this question. What percent of the class did better than student A? Now, it turns out that the answer to this, and I'm going to try to talk us through it in the next slide or two, but it turns out the answer to this question, you may want to print this out and think about it at your own pace, but it turns out the answer to this question is 2.5%. So only a small proportion of the class did better than student A, right? I could flip that and say that student A, child A, did better than 97.5% of the class, right? Student A, child A, did better than virtually everyone. That's a pretty good accomplishment. Now, where does that number 2.5% come from? Well, it's based on the empirical rule that we talked about last PowerPoint. Now, there's our little bell-shaped curve. It's centered at the mean. For this example, right, the average test score is 60. So for this example, it's centered at 60. We want the proportion, or the area, that's more than 70. So we actually want that area that I circled. That's our goal, is to find that. But empirical rule, remember, tells us the area in the middle. So we go 10 out in one direction, that's 70. We go out a symmetric distance to the left, that's 50. Now remember, for Class A, this is the important idea, for Class A, the standard deviation, sigma, was 5. Which means, right, if I'm going up from 60 in terms of standard deviations, I go to 60 to 65. That's one standard deviation. I go from 65 to 70. That would be 2 standard deviations, right? So 70 is the mean plus 2 standard deviations. Similarly, 50 is the mean minus 2 standard deviations. So, right, the empirical rule tells us 95% of the area is within 2 standard deviations of the mean. So for this picture, for this example, that middlemost area is 95%. But we want the area of that tail, of that rightmost tail. This is very, very similar to the fourth example we did in the last PowerPoint. If 95% is in the middle, then 1 minus 95%, which is 5%, is left over. That 5% gets split evenly between the two tails. So if I take that 5% and I split it in half, I get 0.025, which is 2.5%. That's why the area to the right of 70, right, the percent of the class that scored more than 70, the percent of the class which scored more than child A, is 2.5%. Now what about child B? What percent of the class did better than child B? It turns out the answer is 16%, which is still a pretty good score, agreed? That's saying that child B did better than 84% of the class. I'd be pretty happy if my child did that well. But again, it's not as good as child A. Let's try to motivate where that 16% comes from. Again, I have my bell-shaped curve. It's centered at 60. I ultimately want the area to the right of 70, so I circled the area that I'm looking for. Empirical rule is sort of based on that middle area, so I shade that in. What is the area between 50 and 70? Well, remember, the difference between this and the previous problem is for this, the standard deviation is 10. So whereas before, for student A, 70 was 2 standard deviations above the mean, here, because we have a different standard deviation, it's 10, 70 is only 1 standard deviation above the mean. How does that make things different? Well, it means that area in the middle is 68%, not 95%. And it means the area in that tail is 1 minus 68%, which is 32, but I take that 32 and I split it in half. That gives me the rightmost tail, gives me the area to the right of 70, gets the percent of the class that did better than 70, that's the percent of the class that did more than child B. So the correct answer is 16%. So our conclusion is that student A ultimately did better. Why? What's the punchline? How could I have really seen this without drawing those pictures and going through maybe a convoluted logic chain? Student A ultimately did better because even though they both had the same raw score, even though they both had a 70, student A was more standard deviations above the mean than student B was, right? Student A was 2 standard deviations above the mean, whereas student B was 1 standard deviation above the mean. And so in that sense, in terms of standard deviations, student A had the higher score. The big idea that I'm trying to motivate with these examples is this, that to be able to know, to be able to determine, to be able to discern the worth of a raw score, an actual number or measurement, we need to know, 1, is it above or below the mean? But even more specifically, we want to know how many standard deviations is it above or below the mean. And it turns out that there is a formula that allows us to do this by essentially computing something called a standard score. A standard score is just the number of standard deviations a particular observation is above or below the mean. We compute a standard score using the following formula. So a standard score is often abbreviated with the letter Z, sometimes called its Z-score. We take the actual raw score, which I abbreviate with the letter X, and we do X minus mu. That's saying, remember, subtraction is a distance operator. It's saying how far is the observation from the mean, and then by dividing it by sigma, by dividing it by that standard deviation, we're essentially taking that distance and turning it into units of standard deviations. Let's practice. Let's go on another virtual field trip, this time to the Philadelphia Zoo. I hope you brought your permission slips. Otherwise, I know it's going to break your heart, but you're going to have to be left behind. So, let's say we go to the Philadelphia Zoo and we go to the walrus exhibit. And of course, it's a well-known fact that walruses have a mean weight of 3,000 pounds with a standard deviation of 250 pounds. And with this information in mind, I want us to compute the standard scores. I want us to compute the Z-scores for the following family of 5 walruses. The first is baby Flug. So baby Flug weighs 2,250 pounds. Let's find her standard score or her Z-score. Well, That's just x minus mu divided by sigma. It's 2,250 minus 3,000 divided by 250. If I do that in my head or in my calculator, I get the number -3. The -3 is communicating what? The -3 is saying that baby Flug weighs 3 standard deviations less than the mean. How do I know less? Because the standard score is negative. Anytime it's negative, it means that that score or observation is below the mean. What about Hodar? People are always saying, oh, Hodar, Hodar's so big, Hodar's so hefty. Is he in fact so hefty? Right, 3,500 pounds, certainly a lot for a human, but is it a lot for a walrus? Well, that's the type of question a z-score can answer for us. Right? Hodar's z-score is x minus mu divided by sigma, 3,500 minus 3,000 divided by 250. I put that in my calculator, I get 2. It's a positive 2, which means that Hodar's weight is more than the mean or more than average. In fact, it's 2 standard deviations more than average. Is that a lot? Yeah, it is quite a bit. Remember, empirical rule says that most walruses, 95% of all walruses, have weights within 2 standard deviations of the mean. So this is essentially saying, it's actually analogous to kind of student A. What it's actually saying is that only 2.5% of all walruses weigh more than Hodar if we're willing to assume that walrus weight follows that nice bell-shaped distribution. Right? This idea of a standard score or a z-score gives kind of a common currency. This is how researchers or statisticians measure the worth of values. And values like 2 or 3 or -2 or -3 are seen as striking, right? Baby Flug was -3. That's extremely small, right? Most of us would say, whoa, 2,250 pounds? That's an awful lot of weight. Maybe that walrus needs to go on a diet. But that's a really cruel and unfair statement because baby Flug is actually 3 standard deviations below the mean. Remember, 99.7% of all walruses weigh within 3 standard deviations of the mean. So a baby with, or a walrus with a weight 3 standard deviations below the mean is quite rare. Now, of course, baby Flug is a baby, which explains why she weighs so little. But hopefully you get the idea. What about Cinderella? People are always saying, oh Cinderella, you're always such a svelte, dainty princess of a walrus, weighing in at a dainty 2,875 pounds. Is Cinderella in fact so dainty? Well, we could calculate her standard score. We can calculate her z-score. If we apply the formula, we get -0.5, which is saying that Cinderella weighs half a standard deviation less than the mean. Is she dainty? Not really. Being half a standard deviation is not that far from the mean. So she does weigh a little less than the mean, but fairly close to it. We might say that Cinderella, right, is probably a good, healthy weight. So good for her. What about Goldilocks? People are always saying, oh, Goldilocks, you don't weigh too little, you don't weigh too much, oh, Goldilocks, you weigh just right. Is that true? Does Goldilocks really weigh just right? Well, let's calculate her z-score. 3,000 minus 3,000, really at this point divided by who cares, right? Because 0 divided by anything is always 0. Oh, shoot. There's a typo in my notes, and I apologize for that. I should have caught that. This is the same as saying, right, it's not true that Goldilocks weighs 3 standard deviations less than the mean. That's wrong, right? The standard score of 0 means that Goldilocks actually weighs exactly what the mean is. I apologize for that typo. At this point, I'm committed to narrating it, and I can't really change it without having to re-narrate everything. But hopefully we're all okay with the fact that that last bullet point's wrong. Goldilocks weighs exactly the mean. She weighs 0 standard deviations away from the mean. Here's our last walrus. Bartleby, all the zoologists, all the animal trainers, they're always saying, oh, what a horrible, monstrous, foul-tempered beast Bartleby is. He has such a black heart. Never has there been a more black-hearted walrus, they say. In fact, his nickname is Black Bart. Is Black Bart, in fact, really such a beast? Well, let's calculate his z-score. 4,250 minus 3,000 divided by 250 equals 5. Wow. 5. 5 standard deviations. 5 standard deviations more than the mean. Remember, 99.7% of all walruses weigh within 3 standard deviations. Bartleby is way beyond that. This is like a once-in-a-lifetime walrus. This is like the Halley's Comet of walrus. Right? This is like Walruszilla. This is a phenomenal walrus. 5 standard deviations, something being 2 standard deviations from the mean is fairly phenomenal. 3 standard deviations, very, 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 very rare. 5 standard deviations, almost unheard of. I think that last bullet point sums it up. Wow. What an incredible field trip. And could you imagine if you went to the zoo and they had a plaque and all that plaque said was that Bartleby weighs 4,250 pounds. You probably would just read that and say, whatever, because you would have no idea of the meaning of that number. You would have no idea of the context of that number. You wouldn't know that you're looking at a once-in-a-lifetime walrus. And you would walk by without even appreciating his monstrosity. But if that plaque instead told you that Black Bart had a standard score, that Black Bart had a z-score of 5, you would stop. Your eyes would widen to the size of dinner plates, and you would probably stare at that walrus for quite some time. You might even take its picture and post it on Facebook. Yeah, that's how incredible a walrus it is. And the standard score is our way of being able to discern or determine that. Now, occasionally, we might need to reverse that formula. So, all the examples that we did previous to this, I gave you the walrus's weight, and I asked you to determine their z-score. This is a different question. Here I'm giving you the z-score, and I'm asking you to determine their weight. Now, you could actually just take that formula that we had a few slides back. Z is equal to x minus mu divided by sigma. It's not like you need to necessarily memorize a second formula. If you take that formula and you solve for x, you'll get the second bullet points formula right there. That is, if you solve for x, you'll get x is equal to mean mu plus z times sigma, or z times the standard deviation. Right? Which is a very intuitive score, because it's, remember, the z-score is how many standard deviations above or below the mean it is. So by multiplying the z-score times the standard deviations, that's how much I need to basically add or subtract from the mean. So in this case, Fishy's z-score is 1.75. Fishy weighs 1.75 standard deviations more than the mean. So what is 1.75 standard deviations? Well, that's what the 1.75 times 300 is telling me. That gives me 525. So 1.75 standard deviations is 525 pounds, and he's that much above the mean. So I take that 525, I add it to the mean. I add it to the 3,000, and I get 3,525. And that, my dear friend and fellow student, is how we conclude Chapter 2. Hopefully you had as much fun with it as I did.